Thank you very much for the invitation to come and talk here. I'm very impressed by the algorithmic biology lab and the achievements. Congratulations to the students and to my friend Pavel, yet another very impressive leadership that Pavel is doing. And being in such a cultural city like St. Petersburg, I'm wearing my Van Gogh tie. Okay, so today I'm going to talk about a problem that seems to be a long-standing open problem in the genetics literature, and it's a very interesting challenge that somehow it's at the intertwining between discrete and continuous mathematics, which is a very interesting theme. We need to do more of this in computational biology, that intertwining. So, so basically, I'm going to talk about linkage disequilibrium as a very important concept in understanding genetic variation in populations. And the fact that we really don't have a measure that gives the same answer if you measure in this room or in my room at the hotel. So it's still a very funny situation that there seems to be no unit of measurement that is consistent. So there is a search for measures, and each one has its own way of doing things, and it's very hard to find a framework in which you can put them on a similar footing. So what happened, like with many such puzzles, the literature contains axioms, DESIDERATA, that scientists proposed for the measures to satisfy. But each measure somehow satisfies different properties. So the question is, can we find measures that satisfy jointly such properties? So I'm going to show you progress that we did on some of those questions. So this is joint work with Fumei Lam, who did a postdoctoral stay in my lab, and with my PhD student Ryan Tarpine, that just graduated this year and went to Google. I think Fumei is still applying for jobs. She's on the market this year. So I'm going to talk a little bit about linkage disequilibrium and some of the measures proposed. And some of the axioms proposed in the literature for what measures should satisfy in an attempt to unify the search for such a measure. And a solution that we found, a measure that satisfies some of the axioms, some of the most important axioms, and somehow how the search progressed discovers this measure. We are still in the process of really understanding how good the measure is after satisfying those axioms. And in particular, we looked at applications of the measure in the area of tagging SNP selection, imputation, and so on. So we need to imagine that we have a population of individuals, and for now imagine that every individual has only one haplotype, just for the simplicity. And if we are considering, let's say, 3 loci on the haplotypes of all the people involved, let's say locus A, B, and C, and the alleles, the versions on the genome at A, let's call it A0, A1, and so on, similar for B and C. So if we look at one haplotype of one individual, and we see the corresponding loci A2, B3, and C1, we denote in this way just a sequence of the 3 alleles, the haplotype of the individual at those 3 sites. So the concept of haplotype is apply to a region on the genome, could be the whole chromosome or could be one SNP only, you still call it a haplotype. So in our case, we have these three loci, so this is the haplotype. So being a population of individuals and three sites, we can compute several probabilities associated, several frequencies. So if I have a particular haplotype, let's say the kth allele at A locus, the jth in the B, and the kth in the C, we can denote the frequency of this haplotype in the population by Pijk. And in this way, we have now for every haplotype a certain frequency of the haplotype occurring in the population. So this is like going horizontal. Now if we go vertically, for each allele, we can, for each locus, we can compute the probability of the frequency of a certain allele in population. And we're going to define, because it's loci, pi, the I, dot, dot, which means I don't have the other two. So in this way, we can define p dot j dot, which means I am looking only at the jth allele, and the p dot dot k. It's a standard notation. And of course, marginally, we can compute what this is just a sum over the probabilities, the frequencies of the haplotypes when we sum over the other two indices. So the fundamental concept of linkage equilibrium is independence. And what it is that when for all ij and k, we have that the frequency of the haplotype is actually the product of the alleles the haplotype is defined by, then we call that the three loci are in linkage equilibrium. So it's a kind of independence, randomness going on there. So the interesting part is when there is no linkage equilibrium and there is linkage disequilibrium, sometimes called gametic phase equilibrium or allelic association. So the deviation from random and measures to understand how far we're deviating from random, and this is the subject of our talk. So a number of measures were proposed. How do you measure how far you are from random? And of course, when we talk about populations of individuals, we have to assume some population genetic model. How are those people related to each other? And it's an extremely beautiful theory of various levels of assumptions that progresses towards more and more complex till the jewel of the field, which is the coalescent model. And for each model of population genetics, you are going to have a certain amount of linkage disequilibrium that you expect, because the typical forces of evolution will create such disequilibrium, and there are many forces involved. I'll mention a few as we move forward. In particular, the recombination rate seems to be one of the fundamental parameters to consider. So the concept of linkage disequilibrium is fundamental in many areas of genomics, including the recent and exciting development in genome-wide association studies that put the whole field of finding genes associated with disease traits or with phenotype in general on a different rigorous level than it used before, even 5 years ago. Although it's under a lot of criticism about the fact that what GWAS finds are SNPs on the genome with no apparently biological function. So the mystery of what that GWAS SNP order is telling us continues to be a very interesting and exciting new puzzle, open problem, if you want, in our sense. So I want just to give you a sense in which linkage disequilibrium can be used to find genes associated with disease phenotype, and how this is becoming the modus operandi of how genes are identified through statistical inference based on statistical models of how to infer linkage disequilibrium. So basically, we would like to associate patterns of genetic variation on the genome with phenotype. So if we can find such an association between some patterns on the genome with respect, some patterns in a number of individuals with respect to phenotype that we are interested in, or an association with another locus that is in linkage disequilibrium with the one we are looking at, that's good enough. So that was the idea of GWAS. We're going to find markers all over the genome, statistically randomly distributed, they have a chance, such that if we find some markers that are associated with disease, maybe they are in linkage disequilibrium with so-called causative part. So therefore, if we do it dense enough, we have a chance to start finding association, and then we go from there. So linkage disequilibrium is fundamental in this respect. However, there is no way we can predict linkage disequilibrium patterns on the genome, because this is so much influenced by the evolution of the species considered, and so many other forces, geographic, demographic, that only empirically we can evaluate it. So this is a fundamental property that we have to deal with, but definitely the theory involving estimation of this empirical thing is extremely exciting, and one of the most exciting computational and mathematical development in the last several decades, in my view. So let me just go quickly and introduce two measures that are somehow among the most popular, and start showing a little bit how do we measure deviation from random. So suppose we have a pair of loci, A and B now, and each one with two alleles. So if there is linkage equilibrium, which means the frequencies of haplotypes are just product of the frequencies of alleles, this is the equation that we have. So the deviation can be simply obtained by just subtracting from the probability of the haplotype that you observe in the population. You subtract the random, the deviation from random, and this is the Lewontin D, Dick Lewontin's measure, and there are a number of variations on D, but it became fundamental. And one of the things that we're going to talk is that all the linkage disequilibrium measure happens to be binary. So there is a curse of binarity. The moment you introduce measures for 3 or more, they stop behaving nicely. So there is a fundamental question of how to consider higher order when you have to deal with several markers. How do you measure that thing? But for now, we stay binary. So this is the D, and then there is a second one called R square. Another measure, it's small r, but I couldn't do a small r in the title of my slide. So it's basically R square, which is Lewontin's D divided by the product of all the allele frequencies, the 2 at the first loci and the 2 at the second loci. So this is actually the square of a correlation coefficient. And it's one of the favorite measures of the HapMap project, because of a lot of interesting connections for this measure with issues related to tagging SNPs and informativeness, and so on and so on. So the literature has a number of measures introduced. Here are just a few of those. And among the problems with the measures is that there seems to be no quantitative phenomenon here in which all of them can be somehow unified under some unit of measurement such that everybody measures in some consistent way. So imagine if we have to do only empirical analysis of those patterns and you don't have a measure that always tells you in a consistent way what it is, you get in two different rooms of this hotel different results for the same objects. It's a little bit funny. And continues to be a very difficult way, the correction, the unification towards such a unit of measurement. And I'm going to talk about some of those challenges. So among the DESIDERATA that the literature proposes for measures, they all want the measure to have a quite simple interpretation biologically, to be related to parameters of the population genomic models like recombination, things that make sense. So you don't have, abstract things that are a little bit far away. But fundamentally, mathematically, those are probably the most cited axioms that were proposed to be satisfied by the measures. So the first one is called independence of allele frequencies. So this will mean that if I measure in this room or the other room, I get the same thing. So if I have to measure on the genome, let's say on the human genome in the population, in a certain genomic region, the patterns of LD, I measure in a region there are loci, and each one has a frequency in the population that is surveyed in various populations differ in some way. So it's very specific to the frequencies of those loci here. So if I go to another room, I have another set of loci. They have their own frequency in the population. So the question is, how can you compare two patterns of LD when you are measuring over loci that have very different frequencies in the population? So, and there is a Leontin paper that has an informal argument, which is very beautiful to follow up and prove something there, that in his view, no measure of LD can ever satisfy this. So the implication that there is always some redundancy of, some residual of dependence to frequency that maybe can be coped in some way, but it's very unclear how to do it. Our work is going to provide the measures that satisfy those two axioms together, interpretability of intermediate values, and extension to multi-loci as a conservative extension of pairwise, because the measures are typically pairwise. But the independence of allele frequencies and quantifying each measure, how much they depend on it, continues to be a very interesting open problem. So no single measure fulfills all the desired properties, and the relationship between how measures measure things look quite different. So what follows next, I'm going to introduce to you the measure and to show you how do we prove that somehow satisfy those two axioms. So the first axiom is to give us a sense to interpret what an intermediate value of the measure it is. Typically they are between 0 and 1. It's very easy to interpret 0 and 1, but it's very hard for some measure to know what it means 0.3. So therefore you are going to see that is related very much to the sample size and the power of what you can test in it. And the second one says, you define your measures pairwise. How do you extend it to 3 or more sites in such a way that is not ad hoc what you do? It's a kind of unique extension to many sites. So that's what we're going to do. So the measure is called directed informativeness, and it's a directed version of another concept that we introduced in previous work, which was called informativeness. And the informativeness papers occurred in genome research. And I would like to first show you a little bit of informativeness, because otherwise the directed one will not fit as well. So I'm going to switch for just a second. What did, there are many things here now. Right. Here it is. How do I need to do all right, here it is. Oops. All right. So it's from another talk, but I'm going just to flip a little bit. So this is joint work with Vinit, who we were together at Celera at that time. And this was a problem that Andy Clark brought to us, and it was the curse of the pairwise. And the curse of the pairwise is that the fact that all the LD measures are pairwise, and any attempt to go to three ways analytically explodes. All the goodness properties of the pairwise measure disappear. So what can we do? So the problem that Andy proposed to us was the following. Suppose you need to select tagging SNPs from a collection of haplotypes. And the issue is that you want to create a DNA array, and you want to pick only some tagging SNPs. How do you pick them in such a way that they are the most informative, the minimum informative subset? Which means that if you tag those, the other that you didn't genotype can be inferred through information. So it was the issue of having a haplotype matrix. Every row is a haplotype, every column is a SNP. Find the minimum set of SNPs such that is the most informative with respect to the rest. So we need to define informativeness, but this was a problem in array design that we used. So I'm going to flip through SNPs and mutations and recombination. I'm going to just go to the algorithm. This is how evolutionary we would hope to find so the solution of the algorithm that is going to compute the measure is going to be based on set cover, a graph theoretic approach. And in a very simple example, the minimum informative subset would be, if you have a set of haplotype like this, pick a number of SNPs such that if you have cases in control, the values of the SNPs in the selected window is able to distinguish cases from controls. So you have this idea that you want the minimum set of columns that has this property to distinguish everybody from one set from everybody from the other set. And that will be, it just happened in that example that you need three SNPs. One cannot do a good job when you have the general situation. So I'm going to skip a little bit. So again, the minimum informative subset will be the concept here. So I'm going to understand what this informativeness does, I'm going to try to define concepts of how one SNP predicts another. Because if I want to genotype just very few SNPs such that all the information from those few SNPs implies the information on the others, I want to understand how in one SNP I have information for another. So, and then the problem will be pick the minimum number of SNPs such that you can infer the whole haplotype matrix. So the fundamental insight in an information theoretic sense is like the bit would be the fact that In a more basic sense, a SNP does the following: distinguishes two haplotypes, namely an individual that has 0 at one position versus an individual that has 1 at that position. So if this is the SNP and those are the alleles at the corresponding position, this SNP, this position, in particular does the following: distinguishes those two individuals because one has a 1, one has a 0. That's the fundamental operation. So you want to understand how much distinguishability exists in a SNP, how much distinguishability exists in the whole matrix, and you can say, give me the set of SNPs that have all the distinguishability compressed into those few SNPs. So the concept is very easy. Each time we have a 1 and a 0, we draw an edge in a graph associated with this column, and we call it a distinguishing edge, a D edge. So you could see that the distinguishing edges that can be constructed for every column can be all compressed into one column graph in which you overlap all the edges and you take only one when you have multiplicity. And therefore, there is a graph that represents all the distinguishing edges associated to the whole matrix. So therefore, if you have a subset of SNPs, you can ask what is the distinguishability graph of those set of SNPs. And when you have coinciding with the whole matrix, this means you have an informative set. And when it's the minimum with respect to the number of SNPs, you have the minimum informative SNPs. So that is the concept of the edges and the informativeness that we're going to measure. And I'm going to introduce them now formally. We also wanted that axiom to be satisfied to extend to multi-markers and so on. I'm going to skip over some things. So this is the new measure, informativeness. And at that time, we proposed that we are going to satisfy the following axioms. It needs to extend uniquely to multi-markers. It needs to respect LD consistency, to compare well with other LD measures. At that time, that was very important. The block freedness was actually the main difficulty at that time. We wanted somehow our definition to be independent of concepts of haplotype block, which are notoriously ad hoc, although they all coincide in the interior of the block. The boundaries are very ad hoc, so we wanted something block-free, independent construction. That was another axiom. And of course, we wanted to have a polynomial time algorithm that can compute genome-wide answers, and a statistically sound check not to be overfitting, and so on. So the paper actually constructed this informativeness measure. And I'm going now to just define on an example for you to see how we do those kind of things. So here is column number 1. This is the distinguishability graph. There is an edge between 1 and every other 0, as you could see. Here we have only between 0 and 1s. So it's a bipartite 0s to 1, and so on and so on. So the way in which you think of one SNP predicting another one is saying how many distinguishing edges in S1 that are also in S2 are there, how much S1 can predict S2. So you can, as a fraction of all the edges in S2, how many are in S1, and this is the informativeness. So let's see S1 and S2. So how many edges are in common? There are 2 in common over 4, so you get 2 over 4, 1/2. Of course, you can extend, obviously, to sets, because if you take those 2 together, you union the graph, make it single edge as opposed to multi-edge, and you get the same definition. So it extends uniquely to sets of SNPs and so on. And here is how we solve it in an algorithmic way. There is this minimum set cover formulation. And it turns out that the minimum informative subset is exactly the minimum set cover if you do the following graph construction. The SNPs are the boys and the edges are the girls, and a bipartite boy-girl graph. So the SNPs have their distinguishable graph represented in their vertex, and the edges means the collection of all the edges in the union of all the distinguishing graphs. So for example, I highlight this edge here, this edge. So if you see, there are altogether 6 edges, and that's what the node means. The graph represented in all of those is the complete graph by union of all the vertex graphs, and only the edge that I represent is highlighted in red. And the edges in this bipartite graph are the obvious ones. I just put edges towards the corresponding green edge that is contained in this one. And it turns out that the minimum informative set, which is the minimum number of boys that know all the girls, is exactly the minimum informative set of SNPs that has the distinguishing power equivalent to the entire matrix. And that was the idea. So we showed at that time that there are very nice connections with other measures, including d prime and r squared. D prime is a variation of d that has a certain normalizing formula. And there are interesting connections. At that time, we were just observing that there is a consistency with what an LD measure should look like to behave a little bit like, at least in the endpoints, as the major other measures and so on. So, of course, problems are NP-complete of this type. And in the end, what we were able to do is to have a fixed parameter tractability algorithm that in practice actually worked very well by making an assumption that the window of a set of SNPs that are in linkage disequilibrium is something similar to the block size, and that gave us a kind of, although exponential in general in that parameter, if you assume that that parameter is fixed, you actually can compute by beautiful recurrence, which actually is due to Vinit. And that was the informativeness as a measure. So I'm going to apologize. I'm going to switch back to my talk, especially if I get help from my friend here. Yeah, that's it. Thanks. All right, so I was informativeness. Now we have directed informativeness. So what is now happening, we're going to add a direction to it. Because now we want to satisfy those two axioms. As you can see, the extension to multi-loci was very straightforward, and that is going to continue to be a unique extension. The issue is, how do you connect to the other axiom that we wanted, which was interpretability of intermediary values? So here comes, sorry. All right, so what I have here is just a notation for the standard matrix of haplotypes times SNPs. So n rows, the haplotypes, m columns, the SNPs. The distinguishability edges are in this graph GS, in which I have edges between haplotype I and J, row I and J, at SNP S when they are different. So that was the distinguishability graph. So here is a column for SNP S and the corresponding edges. So at this point they are undirected, and very soon we're going to put a direction on them. So at this point it was just zeros connected to ones in a bipartite way. So this was the undirected informativeness, the one from the previous paper. And we can talk about informativeness of SNP S with respect to SNP T as being what we said. You look at the distinguishing edges that are from GT. You want to predict T from S. See what is in common and divide by all the edges in T. So what fraction of the distinguishing you can find. It is a measure between 0 and 1, like all the other LD measures. So here is S and T. We look what is in common. We compute a number. It just happened here to be the same if you predict T from S. But so here is the next construction is a directed graph. So the only point that we're making now is that edges are directed from 0 to 1, from allele 0 to allele 1 in the same sense. So that's all it is. Here it is, the graph. So now it's a directed graph, again, from zeros to 1. Here is the definition. So now we're entering into some kind of an algebraic count. It's no longer sets. We're going to like quantum mechanics. No, I'm kidding. Some kind of cancellation starts happening, so it's much harder to interpret what's happening. But what is going to be now is the same sense that when you share edges in the same direction, it's a positive thing. When you share edges in the opposite direction, you lose something. So there is going to be an algebraic summing here, and it's exactly what we had in undirected informativeness. But now we have, with edge reversed, to see what is captured but in the opposite direction, and you subtract from the two, and you. So again, we get -1 to 1 the range. So what you do something like this. The red is shared but is in different directions, so you are going to get a penalizing 1 here. So it's very straightforward as a generalization of the other one. How is the extension to multi-loci is just union, is just set theoretic. So it's a unique extension again. So we can do sets again, put those two together, and get now between the haplotypes the corresponding thing in a union fashion by just the union of the column graphs and so on. So you can now extend it to two sets of SNPs between set S and set T in a similar way. So now it satisfies the desired axiom. It's uniquely extended from pairwise to many. So, among the other good properties of the new measure is that there is a beautiful relation to R square. And there are many other analyses. I will not have time to talk today, but I want to show you the Fumé lemma. So this is Fumé's lemma. So Fumé is on the market. She did this beautiful theorem that was very, very moving. So the Fumé lemma says that the correlation coefficient, the favorite R square of the HapMap and the population geneticists, is actually I arrow squared in a symbolic sense. So it's I direct informative from S to T multiplied, to the other way around. So that is what we call it a form of, combinatorial square root of this R square here in that sense, because it's a symbolic in how it is. And because of this relation with R square, and because R square is the model that has interpretable intermediary values, we have now a connection towards that bridge. So, and you'll see why R square is actually chi-square times n, the population, effective population size. So R square and chi-square, which gives you the statistical information about the sample size, are related, and in this way things are connected. So in that sense, we're saying that it's satisfying the in a formal way, the intermediary values property. So there is a very deep result of, to some extent, folkloric in the population genetics literature. There is a proof in Pritchard and Przonski in 2001, which, is something along those lines that quantifies to what extent R² holds the key to understanding the information that you can get by looking at the sample size. So the issue is that tagging SNPs are objects that you select from the set of all of them, but you pick a much smaller set of SNPs to test. So you are losing information in this way. So what R² is telling you, how much do you have to enlarge the sample in such a way that that information is not lost. It's a very, very interesting theorem that is involved. So it's this 1/R² that gives you the loss that you need to cover for. Of course, we can extend it to sets. Now, if you think about directed I² now, which was in the particular case of single SNPs, exactly R², this becomes now a generalization to multi-markers of the pairwise R², which was never extendable to many. So there are many interesting things to continue to analyze of what this is going on. Here is a table of some of the most often cited measures in the literature and the relationship with directed informativeness. This is Fumei's lemma. Here is chi² because R² is chi² times n, of course, but here it is. There are delta things. This is the Luntin D prime, various other things, and so on. One very interesting observation is that there is a very nice understanding from the contingency table associated with our SNPs between permanent of the contingency table and determinant. It's very interesting that almost all the measures are determinant-based, the LD measures. And somehow what we are putting here is a combinatorial component to it. And this is a deep connection in our view, but we didn't get quite far to understand the significance of this. So, it's a sense of unification, at least it looks like, contributing to many other measures and so on. How am I doing with time? Few minutes. So maybe I should stop here and say that maybe a major challenge next would be to try to bring some version of the independence of allele frequency axiom and to search for a measure that satisfies those three. So it's a conquest to go deeper and to understand whether there exist such measures. One thing that we're doing here is that we are moving into the world of computer science as opposed to statistics, which is just formulas and I would say continuous mathematics. What we are proposing is a measure that now has algorithms that are polynomial time, some sophisticated pieces of code, but they compute the right thing that has good axioms. So, to have just simple formulas versus more sophisticated formula, which are algorithm, apparently is a necessary thing. I don't think there is a magic formula that will have 3 lines or something that will capture what is needed. So therefore, looks like a very beautiful problem for an audience like this one, computer scientists and statisticians working together. But it's a fascinating area, and LD is just an extraordinarily inspiring concept. And all the GWAS success is based on LD, so it's really worthwhile spending time and trying to clarify rigorously aspects of LD theory. Thank you very much.
Questions?
Yes.
So then, if I try to generalize this, the next target would be the correlation calculation from multiple points.
So the next one will be maybe the first axiom that we don't know how to do it, which is every measure apparently will have a dependence on the allele frequencies of the region you are measuring. And you would like somehow to move beyond this. So there is this informal conjecture of Dick Lewontin that says any measure will always be dependent on allele frequencies. We need to prove something first. He always has enormous insights. I'm sure it's true, but it may be that there is always true, but maybe there is a level of commonality you can subtract, or some kind of other level of robustness. But it's a very, very interesting idea, even to understand for R square what is the dependence bias that you are not aware when you measure, or D prime or others. So I think that is a very good next step.
Suppose the function values are not binary anymore, some real values.
Multiple alleles, you mean more than binary? Or
maybe not in a allele context. Maybe, let's say, you just describe your entity, not 0, 1, but any value in between.
Yeah. So there is the QTL thing, the continuous measurements, and of course it's a serious theory. But this is a simple enough case that if we cannot solve it, it's before we move to generalization. But I agree, it's an important case. Yes.
I don't know if you say, maybe I missed it. Still, even the directed version isn't complete.
Yes, they are both. Yes, we have a proof for both of them.
Still from self-cover?
It's a variation on the proof on the yes, Vineet?
Could you repeat the question?
The question was, is direct informativeness also empty complete? So yes, we have a proof.